Good afternoon, everyone. My name is Adnan Hamid. I'm founder at CTO at Breker, and this talk is about two portfolios of fast apps that Breker announced today. My background is in CPU verification. I started at AMD and then later at Intel, and found myself pioneering the idea of using planning algorithms to generate test scenarios. First, I took this to the system level, and then now with the advent of RISC-V, maybe we bring this back to the CPU level. The outline of my talk today, we're going to talk a little bit about functional integrity for RISC-V at all, and the differences of the problems we've got to consider when we're trying to verify a core, an individual CPU, versus a system or a SoC built around that CPU. We'll talk a little bit about these fast apps that we've introduced, and discuss a little bit about why Breker thinks they have something to say over here and what we're trying to do about it. Okay? So, functional verification, functional integrity, always a big problem. Our users expect the quality they would get from an ARM or x86 processor, but our builders, we're a little bit smaller in terms of the groups that are building these things. And let's put that a little bit in perspective, right? Okay, some big numbers, right? How big around is the Earth? How many stars in the galaxy, and so on. Against all of that, if you look at how many cycles ARM will spend on each generation of the CPU design, it's a big, big number. How do we catch up? What was all that about? Okay, so what challenges do we have? Okay. We know that the big guys have been investing for 30 years in verification. We know we got to do automation. Nobody here is thinking that you're handwriting all the tests you need. But RISC-V brings us a bunch of unique challenges, right? We like to put in our own little instructions that do something special. We got to be compliant with the standard. I am seeing all kinds of designs from the smallest microcontroller to big superscalar architectures coming out. And different stakeholders have different problems, right? If you're building a little embedded core, you have one set of problems. If you're building a processor cluster that might be, with L1, L2, you have a second set of problems. If you're trying to integrate that into an SoC, you have a third set of problems. And we got to find solutions for both the folks who are developing the cores and the folks who are integrating them. So what's the difference between who are the core developers and the integrity and the SoC guys, right? So we have one population in our community. We're building cores. Some are building little cores, some are building big cores. But we're trying to get the core right? So we've got to make sure the execution pipeline doesn't stumble. Load store is typically 80% of our CPU. We've got to make sure it works right. We've got to deal with silly things like branches and interrupts, which upset our nice, clean execution. Then somebody comes along and takes one or more of our cores and wants to integrate it into a system, and they got a new set of problems to worry about, right? Over there, we got to deal with the whole system integrity issue. So this is coherency, interrupts, power management, and so on. Then we want to do the end-to-end use cases, right? Probably data coming in over something like PCI Express, being maybe processed by the CPU, and then DMA'd out to Ethernet or whatever it is, right? The real use cases that our chip is built for. And we want to bring in early firmware validation, right? We want to be able to test that firmware early in the system. So we need two sets of solutions, one focused on the CPU guys, one focused on the system guys. So let's dig a little bit into the sorts of problems that we see when we're looking at actually validating a CPU core itself, right? Any of you who are designing cores, you know all of this, but let's walk through it anyways, okay? Level 0, okay, we got to get through some random instructions, make sure 1 + 1 = 2. We generate the right flags and so on, right? Over there, I do see some offerings already out there, open source, some commercial. I think random instructions kind of handled. Quickly after that, we're starting to talk about our pipeline register hazards, right? Multi-issue machine, we got to make sure one guy who's just trying to update a register gets there before the guy who's trying to read the register. Write-write registers, write-write hazards, read-write hazards, all of those things, right? After that, we've got to go worry about our load store system. As I said, 80% of our design is load store. Maybe had its prefetch buffers, write buffers, caches, blah, 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 right? So we've got to make sure we hammer it with interesting sequences of addresses to make sure that guy works. From there, we start thinking about branches, right? Because branches suck. They put bubbles in our pipelines. We don't like branches, so we do branch prediction. Got to make sure we got that right. So try all kinds of strange branches. Branches are taken, not taken, all the shadow effects, things that we deal with, right? Okay. Once we're there, then we're going to start thinking about synchronous exceptions. Do our page tables, do our interrupt tables work, right? From there, you're going to worry about asynchronous interrupts, privilege switching, security, virtualization, on and on and on, right? But there's kind of a cascade of things that we got to do. Some of these solutions, maybe each of you have solved, some maybe you're waiting to solve. So what Breker did was we came along and introduced a portfolio of fast apps, each of them targeting one of these line items that you can mix and match as you choose. When you get to the SoC level, the problems are different. Okay, now you're building a system that has probably multiple types of memory, maybe a couple of channels of DDR, some on-chip RAM, some flash, tightly coupled memory, all of these things that we like to do. Okay, can everybody reach every memory that they're supposed to, right? Basic testing. We're building an SoC, we probably have a bunch of uncore IPs in addition to the CPU. Can we just reach all those registers? Did we stitch the damn thing right? Now, our SoC is built to work on interrupts, right? We hand off work to various IPs, and when they're done, they come knock on our door and say, yeah, I'm done, what do I do next? Well, just making sure that the system interrupts are routing correctly is the problem. Then you get into multi-core execution, dealing with memory ordering when you have multiple cores, dealing with atomics or locked operations, right? Who's keeping track of who has what line. You get into system coherency, system virtualization. System security is a big, big problem for a lot of people. Power management is always a problem. And again, what Breker has done is come up with a portfolio of fast apps, each of them targeted at one of these line items, and a growing portfolio as the customers teach us what we really should be doing. And the idea, again, is that you adopt whichever piece of this is immediately necessary to you and then work your way up into other pieces as you need. In addition to the system integrity stuff that I listed, there are two other important things we got to solve that I won't have time to talk to you about, but I want to mention, right? One is these end-to-end use cases. We built this SoC to do something, right? Data comes in from somewhere, it gets processed somehow, gets sent out somewhere. So these end-to-end use cases have to happen at the SoC integrity level. And we want to be able to test our firmware early, before we've booted Linux, before we've got on an emulator. Yes, we're going to build a lot of this on QEMU or some other virtual model, but we've got to make sure that the IP drivers are working correctly with the IP. So all of that we have brought into the solution as well. Great. So on the surface of it, sounds okay. Why would you ever talk to Breker about this? Okay. Breker is a relatively newcomer to this RISC-V community, so thank you for having us. But we've been solving the system-level problem for a lot of customers for a decade. Many of them actually using RISC-V cores, though we haven't focused so much on the cores themselves. What is it that we actually do? Okay. So we have these abstract system VIPs. So these are high-level models of various types of verification intent, written either in C++ for the folks who are coming from the system world, or written in PSS for folks who are coming from the system Verilog UVM world. And we feed it into the synthesis engine that can generate self-checking tests along with a bunch of debug information, so it's easy to debug. And just as in logic synthesis, you write your RTL once, and whether you're going to 12 nanometer or 10 nanometer technology, you just push the button and you get completely separate gates that don't look like anything like each other, but they have the same functionality. The test suite synthesis takes these input models and can synthesize test cases for various platforms that are native to the platform, optimized for the platform. The tests don't look anything like each other, but they have the same intention. So that's kind of our core capabilities. And at the bottom there, you'll see a list of our system VIPs that we've been targeting the big SoC guys with for a while. Okay. And an important point I want to make about the synthesis approach is what that allows us to do is from the same input model, synthesize test cases that run in UVM unit simulations, run in full chip simulation or emulation, and even run in post-silicon, right? I hear a lot about simulation test cases, some compatibility test cases, but eventually this thing's going to be on silicon. You need diagnostics to make it run, and we're able to synthesize all the way to post-silicon. And for those of you who are doing virtual models, we can run on virtual models as well. So let me talk a little bit about the capabilities of the kinds of things we do to give you a sense of the strengths that these technologies bring to RISC-V verification, both at the core level and the system level. So for example, the strategy we followed for coherency verification. Right? We feed into the tool a transition table or a state machine, if you will, representing the cache protocol, right, the coherency protocol. It turns out a coherency protocol is a state machine, is a graph. The tool fundamentally wants to work with graphs. And what we can do is we can use the planning algorithm to say, hey, please pick an end state you want to end up for that cache line, and then do a chain of operations on the same true shared address, but coordinated across multiple masters so that we take the line through various transitions. So that'll give you one scenario, true sharing within the scenario. Then we interleave hundreds of these things and co-schedule in them, right? So generate a whole bunch of them, and across the scenarios, we have false sharing. So the result of all of this is that what I call cache line tearing, right? What you're doing is you're seeing half your cores try to take the first half of a cache line through one set of transitions. The other half of the cores are trying to take the same cache line through different transitions. In the end, it's a huge mess for hardware, and when you go look at your profiling, you see the same, right? So the point is that these are powerful ways of creating scenarios. For end-to-end test cases, right? So we're building these systems, we put a bunch of cores on them, we put a bunch of AI agents on them, we have our DMAs, our other IPs. But ultimately, we're trying to build systems that support certain flows, right? For example, on my little slide, I have possible flows for a camera subsystem, right? So maybe to take a picture, I have to capture an image on a camera, encode it, save it to the SD card, so the lowest arc in that picture. Maybe to look at a picture, I'm going to load the image off of the SD card controller, decode the picture, and send it to display. The viewfinder might entail getting input from the camera, sending it straight to the display, and so forth, right? So these are all different flows through a chip. What this technology is really strong at is saying, okay, if I have only one thread to work with, I can lay down one end-to-end scenario, read the image, decode it, display it, lay down another scenario, capture an image, encode it, save it to the SD card. That's great. If I have available multiple CPUs or multiple threads, now the tool can generate a scenario, interleave, 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 and pretty soon you have a nice dense test that's doing a whole bunch of end-to-end traffic, and the scheduling is all resource aware, right? There's no row over there where the SD card controller is used more than once. The tool is also scheduling memory, right? We'll have our various memories, DDR, SRAM, flash, whatever, and the tool is scheduling at test generation time what memory goes where, okay? If we're doing CPU designs, of course we're worried about where we're using our memory. If we're doing system designs, of course we're worried about where memory is being used and how we create memory conflicts. As Breker evolved and we got, our history in this, right, is very honestly starting in at ARM, right? In October 2013, Apple said they were going to go to ARM 64-bit architectures, which meant ARM v8. Every one of my SoC customers dropped the 32-bit clusters, went to 64-bit clusters. All of a sudden, coherency became a system issue, and none of them could spell coherency. So we started down this journey. And then we kept getting pushed to provide more and more capabilities, to the point where we started to build our capabilities as a set of individual modules that we can plug and play to create customer scenarios very, very quickly that the customer can plug and play. Okay, so this is our background. Along the way, we realized that we had to give the customers ability to extend these things, maybe different ways of allocating memory, specialized algorithms to test their particular SoC, add special instructions, right? We really like to do that in RISC-V. So this extensibility. So this is where we're coming from. And what are these fast apps, right? So looking at the RISC-V community, we need easy solutions that we can deploy rapidly, get solutions going right now, right? Anybody who's building a CPU, you're worrying about your register hazard tests, you're worrying about your load store tests. You can build, or you can just spend the next 2 months building something, or maybe you can just use something off the shelf, right? So these fast apps are pretty much the various individual capabilities that we've had in developed for these big SoCs. First in ARM and then in x86, that are getting packaged into bite-sized pieces, supporting each of these individual capabilities, allowing users to pull them in, use whichever feature they need or any combination of feature that they need. Okay. So that leaves me about 5 minutes for questions, but thank you for coming. Somebody's going to save me with a question, no? Okay, I guess we can tear it down. Yes, Bill? Sure. Okay. Thank you, everybody. Thank you very much.